Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to cover unit vectors and normalization. So, in this topic, we will define a unit vector for a given norm. We will describe the algorithm for normalizing a vector, and then we will introduce the hat notation for finite dimensional unit vectors. Now, if u is a finite dimensional vector, we will say that u is a unit vector if the norm of that vector is equal to 1. This, of course, depends on the norm being used. However, in this course, we will generally be using the 2 norm. Now, if a finite dimensional vector u is known to be a unit vector, we will put a hat on top of it. So, consequently, if you ever see a boldface, lowercase u or v or w, with a cap on it, or a hat, then its norm will be 1, and generally it will be the 2 norm will be 1. Now, note that this slightly differs from other vector spaces where the hat has meant that the expression underneath it describes the vector in question. So, for example, the first vector here, which is a discrete signal, is the value 0.5 to the n, where n goes from 0 to infinity for integer values. The second is the quadratic polynomial x squared. Now, if we are using the 1 norm, then u is a unit vector when the sum of the absolute values of the entries equals 1. If we are using the infinity norm, then u is a unit vector when there is at least one entry that is equal to 1 in absolute value, and all other entries are less than or equal to 1 in absolute value. Finally, if we're using the 2 norm, u is a unit vector if the sum of the squares of the absolute values of the entries is equal to 1. We don't really need the square root here anymore because the square root of 1 is 1. Now, using the 2 norm, which is what we're going to use throughout most of this class, in R2, all unit vectors lie on the unit circle. In R3, all unit vectors lie on the surface of the unit sphere. And finally, we will say that in R to the n, all unit vectors will be lying on the surface of the unit ball for that particular dimension. Now, given a non-zero vector u, we can define its associated unit vector by dividing u by its norm. So if u is any vector in a vector space, then u cap is the normalized unit vector. Again, we are going to be almost exclusively using the 2 norm to normalize vectors. So u cap is a vector divided by its 2 norm. Now, you'll remember that this is scalar multiplication. So dividing a vector by a real number is the same as multiplying the vector by the reciprocal of that number. So, for example, here we have a vector 1, -10, 5, 9, 7. The 1 norm of this vector is 32, and so if we were to normalize this vector, we would divide each entry by 32, giving the vector we see here. If we calculate the 2 norm, then we find that the 2 norm of this vector is 16. So if we were to normalize u with respect to the 2 norm, the resulting vector would be what we see here on the lower right-hand corner. Finally, the infinity norm is equal to 10. So normalizing this vector u with respect to the infinity norm is the vector you see here. Again, it contains at least one entry that has absolute value 1, and all other entries are less than or equal to the absolute, that have an absolute value less than or equal to 1. Now, again, in this course, we will be using the 2 norm for normalization. So, for example, here we have a 4-dimensional vector. We can calculate the 2 norm. We find the 2 norm is equal to 2.5, and then we can divide each entry of that vector by 2.5 to get its associated unit vector. Note, the vector u is unchanged. The vector u hat is a new vector that is normalized. It is a scalar multiple of u. So, following this topic, you now understand the term unit vector. You know that we will generally be using the 2 norm to calculate the length of a vector, and therefore you understand the algorithm for converting a non-zero vector u into its associated unit vector u hat. Here's the references, the acknowledgements, colophon, and a disclaimer. Cheers!